So today we start the next lecture of complex numbers. In the previous lecture, we have studied about properties of modulus in complex numbers. Now we move to equation of a straight line. Joining 2 points Z1 and Z2 in the complex plane. So equation of a straight line in a complex plane is A bar Z plus A Z bar plus C equals 0. This is that if we have a line AB, it is this one A of Z1, this is B, this is Z2, and this is another line B, this is Z. Okay, so if we talk about this is the general form of a straight line. Straight line. And if we found from this, we get a straight line is Z times Z1 bar minus Z2 bar minus Z bar Z1 minus Z2 plus Z1 Z2 bar minus Z2 Z1 equal to 0. This is the required equation of the line. Now we'll move to equation of a circle in a complex line. Equation of a circle. So that the equation of a circle in the R1 plane can be put in the form Z bar plus B bar Z plus C equals where C is real and B is complex. This is complex constant. So this is the general equation of circle in complex. Now equation of circle passes through 3 points Z1 Z2. The equation of circle passing through 3 points Z1 Z2 Z3 H Z minus Z1 upon Z minus Z upon Z3 minus Z1 upon Z3 minus Z equal Z bar minus Z1 bar upon Z bar minus Z2 bar upon Z3 bar minus Z1 bar upon Z3 bar minus Z2 bar. So this is the equation function T passes. If there are 4 points, then just replace Z by Z. Likewise, we can write 4 points. If it is given that 4 points, Z1, Z2, Z3, Z4 are coinciding. If Z4 minus Z1 upon Z4 minus Z upon Z3 minus Z1 upon Z3 minus Z2 equal Z4 minus Z4 bar minus Z1 bar upon Z4 bar minus Z2 bar upon Z3 bar minus Z1 bar upon Z3 bar minus Z2. This. Now angles between two lines. Angle between two lines. It's theta. That is which is lies between minus pi to pi. Each angle between the line AB and C, where A of Z1, B of Z2, C of Z3, D of Z, then theta will be, this angle will be argument Z1 minus Z2 upon Z3 minus Z. This is the angle between two lines, AB and CD. Now there are some results. So this is the general formula for angle between two lines AB and CD. So here the first result is that if AB is perpendicular to CD, then argument of Z1 minus Z2 upon Z3 minus Z is plus pi by. Okay, or we can say Z1 minus Z2 upon Z3 minus Z2 equal to purely imaginary number. Purely imaginary number. Now the result points A, B, C, D are collinear if Z1 minus Z2 upon Z3 minus Z4 equal real. If these are perpendicular, then its argument will be half, pi by 2. Yeah, we can say this will be purely imaginary. And if it is real number, then we say that these 4 points are collinear. Okay, now we move to next. Inverse point with respect to a shell. Inverse point with respect to a shell. Now, the points A, Z equals A, and B, Z equals to B are said to be inverse form of a circle with center O and radius R. If O, A, B are collinear, and OA into OB equal R square, then we have to show that A minus Z0 into B minus Z0 equals R square. This is OA, this is OB, so it's kept in it. So then argument of A minus Z0 equal argument of B minus Z0 equal over minus argument of A minus Z0. This gives argument of A minus Z0 plus argument of B minus Z0 bar will be 0. Now, this implies A minus Z0 times B minus Z0 bar here and equal to R square. Hence, A minus Z0 B minus Z0 whole bar equal R square is the required equation. So this is the equation of inverse point with respect to a circle. Now from this we can deduce it. So there is some deduction. First one, if Z0 equals 0, then A and B are inverse point. AB are equal R square and Z1 Z2 are inverse point of the circle of Z equal to R. If Z1 Z2 are equal R square. Finally, Z1 comma 1 upon Z1 are inverse point of modulus of Z equal. Second, if Z equal to 0 and Z equal to infinity are inverse point of mod Z equal to 1. Z equal to 0 and Z equal to infinity are inverse point of Z equal to 1. Now we move to some examples. So that the triangle whose vertices are Z1, Z2, Z3 and Z1 dash, Z2 dash, Z3 dash are directly similar if Z1, Z1 bar, Z1 dash 1, Z2, Z2 dash 1, Z3, Z3 dash 1 equal 0. You can see how we prove it. We have to prove it. Okay. So let the complex coordinates of vertices triangle ABC and triangle A dash B dash B dash B. For ABC this is Z1 Z2 Z3 and for A dash B dash C dash it is Z1 dash Z2 dash Z3 dash. Now AB will be Z2 minus Z1. B.Sc will be Z3 minus Z2. A dash B dash Z2 dash minus Z1 dash B dash C Z3 dash minus Z. Now triangle ABC is similar to triangle B. This condition giving both triangle are similar to triangle A dash B dash C dash. So this implies that AB will be the lambda times A dash B dash. Likewise, BC will be for lambda times B dash C dash. Okay. So now this implies that we can see here this implies that Z2 minus Z1 equals lambda times Z2 dash minus Z1 dash. Likewise, Z3 minus Z2 equals lambda times Z3 dash minus Z2. Okay. So from here we get the value of lambda is Z2 minus Z1 upon Z2 dash minus Z1 dash equals lambda. Z3 minus Z2 upon Z3 dash minus Z2 dash equals lambda. From these two, so from here this is equal to lambda, this is equal to lambda. It means both these are equal to each other. Means Z2 minus Z1 upon Z2 dash minus Z1 dash equal Z3 minus Z2 upon Z3 dash minus Z2. Okay, we can solve it. So this implies that Z2 into Z3 dash minus Z2 dash. Now, so from this we get Z1 times Z3 dash Z2 dash minus Z2 minus Z2 Z2 dash minus Z3 dash plus Z3 Z1 dash minus Z2 dash equal to 0. So we can write it Now we can write it Z1, Z2, Z, Z1 dash, Z2 dash, Z3, 1, 1, 1 equal. And so now we move to next. Determine the region of argon diagram given by this. Modulus of Z square minus Z less than 1. Now we can solve it. We know that Z equals R e to the power I. So Z square minus Z will be R square e to the power 2I theta minus R e to the power I theta. We can write it like that R square. This can be written as cos to theta plus iota sine theta minus R times cos theta plus iota sine theta. We can write it like that R square cos theta minus R cos theta plus iota R sine R square sine theta minus R sine theta. Now the modulus of Z square minus Z will be square root of R square cos theta minus R cos theta whole square plus R square sin theta minus R sin theta whole square. Now scaling both the sides we get Z square minus Z whole square equals R square cos theta minus R cos theta whole square plus R square sin theta minus R sin theta whole square. Now we can solve it. So Z square minus Z whole square equals R to the power 4 plus R square minus 2R cube cos 2 theta cos theta minus 2R cube sin 2 theta sin theta. So again we can solve it, simplify it. We get modulus of Z square minus Z whole square will be R to the power 4 plus R square. We can take 2R cube as common. So this is the cos A plus cos A minus cos B. So this will be cos 2 theta minus theta. So that will come R to the power 4 plus R square minus 2R cube cos theta. We know that this will be less than, so Z square minus Z whole square less than 1 when R to the power 4 plus R square minus 2R cube cos theta less than 1. So it means r to the power 4 minus 2r cubed cos theta plus r squared minus 1 less than 0. Hence, the region is the interior of the curve. Hence, the region is the interior of the curve r to the power 4 minus 2r cubed cos theta plus r squared minus 1 less than g. Now we move to next. If modulus of a minus b upon 1 minus a upon b less than 1, then modulus of a less than 1 and modulus of b less than 1. Let a equal to r e to the power I theta and b equal to capital R e to the power I phi. Show that modulus of h r and modulus of b is capital. Okay. Also that a minus b of 1 minus a bar b is less than 2. To prove that modulus of a is less than 1, modulus of b is less than 1, we have to prove that R is less than 1 and capital R is less than 1. Okay. So now A minus, first we find the value of A minus B. So it will come R e to the power I5 minus capital R e to the power I. Okay. So we this is sorry, R e to the power I theta minus R e capital R e to the power I. So by Euler rule we can write it cos theta plus I sin theta minus capital R cos phi plus I sin phi. Now getting the real and imaginary part. So we can write it like that R cos theta minus R cos phi plus iota R sin theta minus capital R sin phi. Okay, this is the value of A1B. Now we can find its modulus. Okay, so its modulus will be A minus B whole square. That will have R cos theta minus R cos phi whole square plus R sin theta minus capital R sin phi whole square. Okay, we can solve it. So what we get modulus of A minus B whole square will be, this will come R square plus capital R square minus 2R cos theta cos phi minus 2 capital R sin theta sin. So it will become R square plus R square minus 2R cos theta minus phi. So this is the value of A minus B. Now we find the value 1 minus A bar B. A bar means conjugate of. Okay, so just put the value of A bar and B bar here. So what we get 1 minus A bar, that is the value of it R e to the power I theta. So it will be just replace I with minus iota. So we get R e to the power minus I theta. And the value of is capital R e to the power I phi. Okay. Now it can be written as 1 minus R R e to the power iota phi minus theta. So it can be written as 1 minus R R cos theta minus phi plus I sin theta minus phi. It can be written as minus theta minus phi. It will become 1 minus R R cos theta minus phi plus I R R. R R is common. Now its modulus will be its modulus will be 1 minus a bar b whole square will be 1 minus r cos theta minus phi whole square plus r sin theta minus phi whole square. We get 1 plus r square minus 2r cos theta minus phi. Now we have a minus b upon 1 minus ab less than 1. So its whole square will be also less than 1 means a minus b whole square will be less than 1 minus a bar b. So just put here. So it is r square plus r square minus 2r cos theta minus phi, and this is 1 plus r square capital R square and minus 2r cos theta minus phi. So it will come r square plus r square minus 1 minus r square is less than 0. So this implies r square minus 1 into 1 minus r square less than 0. So this is possible only. This is possible only if r is less than 1 and capital R is less than. So this we have to fit. So